Hello, welcome to our video solution for problem 15, the final problem, an optional one from Superquiz 2. So this is another problem dealing with equivalence relations, and here we're trying to show a fundamental property of equivalence classes, namely, if you take the equivalence classes of two elements, then those classes are equal if and only if those elements are related, i.e. their pair is in the equivalence relation. All right, so let's see if we can't do this. So let's start by assuming that two equivalence classes are the same. Well, it's going to help if we know what an equivalence class means. So the equivalence class of A is equal to the set of all elements, let's call them X, in the set, such that A comma X is an element of, in this case, our equivalence relation is E. Right? So we're just looking for all elements which are related to A. That's what the equivalence class is. So if we assume that the equivalence class of A is equal to the equivalence class of B, it follows that every element of A is an element of the class of B, right? And vice versa. So in particular, then since, well, by reflexivity, we know that A comma A is in E, and this implies that A is an element of its own class, right? Because now this A works as one of the X's. A comma A is an E. So A is in the equivalence class of A. But the equivalence class of A is equal to the equivalence class of B. So we know that little a is an element of the class of B. Hence, well, what does it mean for little a to be in the class of B? Okay, it means that, well, to be in the class of B, you would need that B comma A is an element of E. But of course, E is an equivalence relation, so we have symmetry. So by symmetry, all right, by the way, up here, right, we might have noted, right, this is reflexivity. By symmetry, A comma B is an element of E. And that's actually what we were trying to show in that first direction, right? So if A and B give you the same equivalence class, then A comma B is in the equivalence relation. Okay, let's try to show the converse direction. So conversely, if A comma B is an element of E, we'd like to show that A and B generate the same equivalence class. So this requires us to show that every element in the class of A is an element in the class of B and vice versa. Okay, so we're going to show one direction, the other will just follow by the exact same argument with all the letters switched. So we want to show, for example, that the class of A is a subset of the class of B. Okay, why is that true? Well, we're going to show if I have an element from the class of A, it's an element from the class of B. So since if X is an element from the class of A, well, what does that mean? It means that A comma X is an E. Then A comma X is an element of E. Okay, but by symmetry, okay, so, and by symmetry, we can turn that around. X comma A is an element of B. Okay, so now though we have these two pieces to the puzzle. X comma A is an element of E, and A comma B is an element of E. And notice these share the same, this A, right? One in the end and one in the beginning. And so we can now use transitivity. So transitivity implies that X comma B is an element of E, right? We have XA and AB, therefore XB is an E. Okay, and so then we can just use symmetry one more time. Symmetry again implies that B comma X is an element of E. And that's what we need in order to show that X is an element of the class of B. Thus, X is an element of the equivalence class of B. So we've shown that if we have an element in the class of A, it is also an element of the class of B, confirming that the class of A is a subset of the class of B. All right, and the exact same proof, which we don't need to write down, we can just say similarly. All right, you just make the exact same arguments. The class of B is a subset of the class of A, and hence the class of A is equal to the class of B. And that completes the proof, and that completes Superquiz 2.